Given the zeros of a polynomial function f and at a point c, f of c on the graph of f, we're going to use the linear factorization theorem to find the polynomial function. Step 1, we're going to use the zeros to construct the linear factors of the polynomial. Step number 2, multiply the linear factors to expand the polynomial. Step number 3, substitute c, f of c into the function to determine the leading coefficient. Number 4, and then simplify. For example 7, we're using the linear factorization theorem to find a polynomial with given zeros. We want to find a fourth degree polynomial with real coefficients that has zeros of -3, 2, I, such that f of -2 is equal to 100. So, because we know that x equals I is a zero, then by the complex conjugate theorem, we know that x equals -I is also a zero. So since we are looking for a fourth degree polynomial and now have 4 zeros, we have all 4 factors. So let's begin by multiplying these factors. Well, the first thing we need to take a look at, okay, well the first zero is -3, so we know that C1 is equal to -3. We know the next zero is +2, so C2 is equal to 2. And then we know that we have another zero, which is I, so C3 is going to equal I. And then we also know that by the complex conjugate theorem, we have another zero at -I, so therefore C4 is equal to -I. And then in the theorem, we're going to write out what that formula represents. We have f of x, which is equal to a, times x minus c1, times x minus c2, times x minus c3, times x minus c4. Now remember that we go to 4 because we know it's a fourth degree polynomial. So now we're going to plug in c1 to be -3. So it's x minus -3. We know that c2 is 2, so it's x minus 2. We know that c3 is I, so it's x minus I. And then we know that c4 is -I, so it's x minus -I. Now what we're going to do is we're going to simplify these signs. So this becomes f of x, which is equal to a. This becomes x plus 3 times x minus 2 times x minus I. This becomes x plus I. And now what we want to do is we're going to write f of x is equal to a. We need to multiply x plus 3 times x minus 2. Well, that gives us x squared plus x minus 6. So you're going to have to FOIL, use the box method to get that result. And then we have x minus I times x plus I. And when we multiply that out, which is the difference of squares, we get x squared plus 1. Now again, we still have f of x, which is equal to a. We don't know what a is, but then we can multiply these two by using the box method. So when we multiply those together, then we end up getting the polynomial x to the fourth plus x cubed minus 5x squared plus x minus 6. Now this is our function. Now the next thing we need to do is we need to figure out what is the value of a. In order to figure out what the value of a is, we need to use the point that was given at the beginning of the problem. So we need to find a to ensure f of -2 is equal to 100, which means the input x would be -2 and the output f of x is going to be 100. So what we're going to do is we're going to substitute x equals -2 in for x, and then we're going to substitute f of x to be 100. So therefore f of x is going to be 100. So we plug in -2 in for x, and then we follow the order of operations. So we have a times -2 to the fourth power plus -2 to the third power minus 5 times -2 to the second power plus -2 minus 6. Now when we use order of operations for that result, that is going to give us our -20. So we get 100, which is equal to a times -20. Divide both sides by -20. 100 divided by -20 gives us -5. So now we know that a is going to equal -5. And now step 3, We're then going to rewrite the function by replacing a to be negative 5. So by doing that, we now know that a is negative 5, so a becomes negative 5, and that's going to be times x to the fourth plus x cubed minus 5x squared plus x minus 6 from this result here. And then we're going to distribute the negative 5 to all of those terms. So we end up getting f of x, which is equal to negative 5x to the fourth minus 5x cubed plus 25x squared minus 5x plus 30. Now, if 2 plus 3i were given as a 0 of the polynomial with real coefficients, would 2 minus 3i also need to be a 0? And the answer to that is yes. When any complex number with an imaginary component is given as a 0 of a polynomial with real coefficients, the conjugate must also be a 0 of the polynomial.